Okay, so thank you for the introduction, and thank you to Javier for inviting me and giving me this opportunity to give this talk, and also to have a look at the campus, to which he gave me a tour yesterday. And I got very jealous, not only for the opportunities that you have here to perform research at your own pace, and but also for the lovely environment that you have here. That is always very inspiring. So, regardless of the circumstances, we all do research, and we do it for very often very specific reasons. In the case of the analysis of structures, on the assessment of their condition, on their performance, we have to deal with some very specific and very serious problems. They're related to the development of damage and the degradation at the material level of existing buildings. Okay? So we have many different actions that impose a burden on the structures. We have seismicity, movement of the soil, either dynamic or static, caused by tectonic earthquakes, and more recently in Switzerland, in the Netherlands, also in the United States, where we have gas extraction, oil extraction, things like that, mining. We have human-induced seismicity, which can cause, of course, severe demand on existing structures. We also have environmental degradation from climatic conditions, from pollution, from chemical contamination of the materials, which, okay, in masonry structures is not just such a serious problem. It can cause superficial degradation, but doesn't very often endanger the condition of the structure. But in a reinforced concrete structure, where the main source of the weakness is, of course, the reinforcement, this can be a severe problem. And of course, we have problems with fatigue and creep. Fatigue, of course, is a very big problem in infrastructure, mostly in bridges, which are subjected in repeated loading. And of course, creep in historic structures, in heavy structures, subjected mainly to compression. This can lead to admittedly spectacular, but very serious collapses, such as has happened in historic buildings in the past. All of these things can deteriorate the condition of the structure. It can cause loss of architectural and cultural value, and it can lead to loss of life. And of course, we do not want to have any of that. So this is all related to damage. We all know what damage is, but let's start with a basic definition of it. So it is a change, a degradation of material or geometric properties that affect essentially stiffness and strength. Okay, structural performance. Of course, we need to define what structural performance is. Okay, we know what damage is, but we do not really know how to quantify it, how to relate, let's say, one physical variable that we measure to a degradation of the strength and stiffness. And why is this important? Of course, I really don't need to tell you, but let's remind ourselves of what we are doing here. In, let's say, in the area of the management of infrastructure, of buildings, what we want is to maintain a certain level of structural performance, which is affected by the onset and the development of damage. At the levels where the damage is not really visible in the structure, such as when we have corrosion of the reinforcement, which can cause cracks in the interior of a building. This does not affect performance very much, but we also cannot really see it. At the point where corrosion damage is so severe that we can see it, structural performance, let's say a quantitative index, has degraded quite a bit. So why is it important to detect the damage while it is still limited? Because it can be counteracted with simple interventions, technically, economically, beneficial interventions, and interventions that do not take too long and are not too disruptive. Of course, when we rely only on visual inspection to intervene and to strengthen or repair, then the cost of maintenance, of course, is much higher. So this is what we want to avoid. We want to have some sort of metric for the performance index, and we want to be able to detect the damage before it becomes too serious. We have basically two avenues, okay, two groups of methods that we employ. Both very useful, both very important. So first of all, we have non-destructive examination, evaluation, testing, however you want to call it. It's kind of like a spot test. Okay, you go once to the structure, you inspect, you collect some data, and then you relate it to, or you input it to some sort of computational model in order to determine, to assess the condition of the structure. Okay, so this is all quite manual, very hands-on. You go, you collect, and then you go and process. You might, in fact, induce a little bit of manual excitation on the structure in the case of, let's say, dynamic identification, or you might rely only on ambient excitation. The instrumentation is usually simple, not cheap, but simple, just to apply and collect the data. We do a spot data collection, and then we go back to the office and we do the diagnosis based on some sort of mathematical model. We interpret the results that we get and we perform an analysis. So this is all very good. This is critical, in fact, in many, let's say, situations, but it does not tell the whole story. If we want to have the whole story of what is going on in a structure, of course, we need to monitor it. We need to be able to see the degradation happening in real time. We need to monitor some sort of physical parameter, some sort of physical property, and relate it to some sort of performance index. Okay, what are the things that we usually measure? Okay, temperature, displacements, strains, some other things that we will see later on. The instrumentation for this is a little bit more involved, let's say, because it also involves the collection in real time of the data and the processing of the data in real time. And this imposes a few more, let's say, requirements in terms of supplying all of these systems with electricity, some sort of connection for transmitting the data. And of course, the processing of this data, since it is real time, it is dynamic, it's a little bit more involved. It involves some sort of signal processing to cancel out, let's say, periodic or temporal effects, to be able to extract some features, some of the features of the response, and to be able to quantify it. Relate the measurements of physical properties to a material or a structural property. And of course, a lot of people nowadays are talking about digital twinning. I don't think that anyone has actually done it yet, but we are getting there. And the only way to do it is through monitoring. Okay, to have some sort of digital representation of an object, of a building, interacting, having a model interacting with direct measurements. And the benefit of all of this is that in real time we can take decisions on whether we need to intervene, on whether we need to evacuate a building, on whether we have to repair. So having an early detection system for the damage allows us to perform at the optimal time in order to reduce cost and reduce the disturbance to the structure. So this is where let's say the concept of quantification of damage comes in. We need to be able to relate, have a constitutive relation between the data that we collect from sensors and to some sort of performance parameter, okay, or a percentile loss of the stiffness or the strength of a material. Now, I think this is where things are getting a little bit complicated. It is a kind of an aphorism, but I think that it is relatively true, that we do not really have a direct relationship between the data that we extract from ordinary off-the-shelf sensors and, let's say, a material parameter that we can use in our computational model for the structure. So the data that we get from the sensors, we have to get through a lot of intermediate steps before we can have a proper analysis of the structure. And if you want to have a real-time model of the structure, this is quite a bit of an obstacle. So we're not there yet, I think, with off-the-shelf sensors, which also are characterized by an additional series of limitations. Okay, off-the-shelf sensors, like strain gauges, I'm particularly thinking about strain gauges, they have a very poor responds to damage. If a structure is damaged in one point, it is very difficult to capture this effect with a strain gauge. They feature very low sensitivity to real damage in the structure. They also have quite substantial costs for installation and for maintenance and for replacement, because their durability is not that strong. A strain gauge on a bridge exposed to the elements lasts for maybe 1 or 2 years. And of course we have the problems that we discussed previously regarding complex data acquisition and analysis and sensitivity to environmental conditions. I would also add that they do not really have, the sensors typically do not deform along with the structure. There is an incompatibility problem between the structure and the sensors. So all of this is quite bleak, quite negative, but there are ways to, let's say, go around all of these problems without altering the structure too much. And I think the key to all of this is to have some sort of embedded sensor within the structure, something that is compatible in many ways, something that is compatible structurally with the structure, deforms along with the structure, which means that it has a double, let's say, a double function within the structure, both structural and as a sensor. Something that responds directly to damage, okay, something that gives you a radically different sensing result when the sensor itself is damaged, and something that can be naturally integrated within it. Since the existing materials that we ordinarily use for our structures, mostly steel and cementitious materials, do not feature these characteristics, we need to induce them somehow. And the way to do this is to introduce changes into their microstructure, into the properties of their microstructure. We need to find a way to induce changes in the microstructure in order for the material to express changes in the macroscopic behavior, both as a structural component and as a sensor. These modified materials, in this way, we can introduce to them new functionalities and enhanced performance, both as sensors and as structural components. And we can create materials that we can use as sensors in repair patches in existing buildings. We go directly to the place where we have some sort of damage, where we have registered damage, and we apply this new material, and we have at the same time a repair material and a sensor, either distributed or localized. So, in order to do this, we have to harness a little bit some very classical behavior that is featured in really all materials. And I'm talking here about electrical resistance. All materials or solid materials have some sort of electrical resistance. They respond differently to an induced current. But also the resistance changes depending on the strain, the deformation characteristics of the material. Take, for example, the typical strain gauge. The way it functions is the strain gauge is deformed. The electric current going through the strain gauge needs to travel a longer distance, so there is an apparent change in the resistance of the strain gauge. This is what is called the piezoresistive effect, and it is a feature of really all solid materials. And it is also present in cementitious materials as well. So these are the equations. I don't think it's very interesting to get into that. But what we are mostly interested in is this part over here. The relation between the change in electrical resistivity of a material and an induced strain. If we can somehow control or amplify this effect, we can create materials that are very sensitive in that regard, where we induce a small change in the strain and we get a huge difference in the electrical resistivity. Okay, so this is what we need to do. Being a common feature in really all types of solid materials, it is interesting to extract some very basic features of this performance. Let's say that we have an ordinary material that more or less acts as an insulator. It is not very electrically conductive. If we can somehow disperse within the mass of the material some sort of conductive, extra, additive, we can in fact control the electrical resistivity of this material. The more material, the more conductive material that we introduce inside of the virgin initial material, the more the electrical resistivity decreases. And in fact, at the end, we reach a certain point where we turn it into a highly efficient conductor. But we do not want to make electrical conductors. We want to make sensors. And sensors need to be sensitive to changes in the strain. The point where this happens is what we call the percolation threshold. It is the point where the piezoresistive performance of a material is optimized. It is where it has the highest sensitivity and also the more stable, let's say, readings of the strain. So we want to achieve that. We want to have a virgin material and we want to put as much conductive extra additive inside of it in order to turn it into an efficient sensor. And then, of course, we have to calibrate it. We have to perform coupled mechanical, electrical tests in order to verify that this sensor has been optimized. Okay, so we need to do various mechanical tests. Usually it's done with, let's say, compressive tests to obtain a constitutive relation between the strain and the change in the electrical resistivity. So artificial intelligence is nice, but it's always very important to go back to the physics in order to understand what is going on. So knowing all of this and knowing a few things about the construction industry, we have to decide what sort of material we want to take and to modify. So in my opinion, and in the opinion of many people, cementitious materials are the best option for this. But why is this true? First of all, okay, what is a cementitious material? It's some sort of connecting matrix, some sort of connecting glue, which can be a lime or a cement, mixed with some sort of aggregate, like a sand or a gravel in the case of mortar or concrete, and whatever type of fillers that we choose to include. I'm talking here about conductive fillers, which can be either in the nanoscale or the microscale, or even in the macroscopic scale. And why are these materials exceptionally suitable for modification? I think the reasons are quite simple. First of all, these materials, let's say in contrast to polymers or metals, particularly steel that we use in construction, they feature cracks, imperfections, pores at the microscale, which is what we are trying to modify in order to change the behavior of these materials. Next, since we want the conductive materials to be evenly dispersed within the modified material, we want to have some sort of medium for dispersing. And I think water is one of the best medium that we have to achieve this dispersion. And of course, we need water for cementitious materials. And the final reason is that we use cementitious materials for everything. Okay, for structural elements, for rendering, for pavements, in bridges. So the scope of applications is enormous. Okay, we can monitor strain, we can monitor temperature in a distributed way, we can monitor traffic in bridges, we can use them for really whatever we want. So what sort of options do we have for modifying these materials? I think most people have worked with three sorts of materials, two of them because they are easy to use, and the third one because it is quite popular. And I'm talking about graphite powder, a material that costs really nothing and you can find it everywhere, but it has some beneficial and interesting properties for us, which is namely the high electrical conductivity. Okay, anything based on carbon is going to be very, very electrically conductive. Next, we have carbon microfibers. Okay, we're not talking about long fibers coming in tows, but we're talking about chopped microfibers, something that can be dispersed in the material and create a conductive network. They also cost nothing. They're very light. Okay, And also they have a very high aspect ratio as a filament. They are of course like a thread. And what we know is that when you create a composite material and you want to modify its properties, when you introduce a filler that has a high aspect ratio, you need a much smaller percentage in order to modify it efficiently. Graphite is not characterized by this high aspect ratio, but it is of course very easy to obtain and to disperse. And finally, we have carbon nanotubes, which are again filaments, which is what we want to see. Of course, with a diameter of a few nanometers. Okay, now we're starting to introduce some difficulties, as we will see later. I mean, they have the properties that we want. They have very high strength, they have very high electrical conductivity, they have a very high aspect ratio, but the difficulties arise when we want to disperse them inside of the material. So what are the ways to obtain an evenly dispersed filler in the matrix? We have to disperse it in the water. Okay, first of all, in order to disperse a nanoscale material in water, one of the simplest methods that we have available is sonication. Through an ultrasonic probe, we sonicate the mix of the water with the nanotubes, for example, in a very clean, very sterile environment. And then we introduce all of the cement and all of the aggregates, and we prepare our specimens. Okay, note here the difference obtained in the color from the presence of the nanotubes. Even at a very small percentage, they modify the color quite a bit. This is something that we need to keep in mind when talking, for example, about historic structures. So this is just with a 1% replacement, or rather addition, of carbon nanotubes in the paste. So this is quite a substantial change. Sonication is a huge bottleneck for dispersing nanotubes in water. Okay, you can try an ultrasonic bath that takes many hours. You can do it overnight. And that is not very efficient. You have to consume a lot of energy, you have to consume a lot of time. You can use a probe sonicator such as this one, but you cannot really sonicate very large quantities of water. And here we're talking about the construction industry. Okay, we need huge amounts of material. We cannot just sonicate a small amount of water and expect to use it in a construction project. So another option is to use chemical dispersants in order to distribute the nanotubes inside of the material, but that has the potential drawback that these chemicals can form an insulating film around of the fillers, which blocks electrical transmission. So it defeats the purpose of modifying the material in the first place. Javier, don't look. These are SHM images, and I know you're very sensitive. But okay, we can in fact determine whether our dispersion efforts have been successful through scanning electron microscopy, which is of course also quite a slow and involved process. So lots of problems. That's why I think when we want to keep an eye on the construction industry, we have to turn to different sort of fillers, especially graphite and CMF, carbon microfibers. Why? What is the benefit? The benefit is not only that they cost nothing and they are very easy to obtain. The benefit is that they can be dispersed, either in the dry ingredients or in the batch water through simple mechanical mixing. Okay, mechanical mixing is something that you can do on site of a construction. You cannot sonicate in a construction site. So really, without introducing any major changes in the fabrication process, we can modify efficiently these materials, either with graphite or with CMF, or maybe even with a combination of the two. Okay, so let's say that we have fabricated these specimens. Of course, we need to take electrical measurements in order to determine the resistance. And we have two ways to do it, depending on the size of the specimen that we want to test. We can either do a two-probe method, which is the easiest to do, where we supply an alternating voltage and we measure the generated current. And we're talking about currents in I don't know, the microampere range, because we want to apply a low voltage and we obtain a low current. Or we can alternatively try a 4-probe method. This is just depending on the capabilities of the lab. I think the results are going to be more or less the same. So we create these materials, cementitious materials, of course, age, and they age quite differently depending on the type of filler that we use. The development of the electrical resistivity is, of course, related to the expulsion, to the loss of water, either through hydration or through evaporation. And, independently of the type of filler that we use, because we use it also in small amounts, we obtain a material at the end whose electrical resistivity is not that different. Let's say at 49 days of age, all of the materials that we modified here, with CMF, with graphite, or with carbon nanotubes, they more or less had the same electrical resistivity. So at first point, maybe at first glance, maybe we were not really successful. But as you will see later, we managed to, let's say, modify efficiently these materials. Here we have a schematic of the sort of material, the sort of specimen or sensor that we create with embedded electrodes over here. I've had many arguments about the material that we're supposed to use. I think it makes very little difference whether you use stainless steel or copper. A researcher said that we should use gold, but I don't think that's very practical. And here we have the experimental setup, where the idea is to apply, let's say, a cyclic compressive load, measure the strain along the direction of the application of the load, and measure the change of the electrical resistivity along this direction. We can also try other different types of specimen sizes, the typical prismatic specimens. These I think are more, let's say, conducive to 4-probe testing due to the dimensions. But the principle is always the same. It doesn't really change. So the effect that we see, or the effect that we want to see, really, is a linear relationship between the applied strain, here in blue, and the change in the electrical resistivity. When you compress something, you reduce the transmission length, and you increase, due to the Poisson effect, the transmission area, so you get a decrease in the electrical resistivity. And this is exactly what we see in really all of these materials. We see more or less a linear relationship until, of course, the specimen starts cracking, at which point, in fact, we had an increase in the gauge factor. This can be an indication, or it can be, let's say, a method of detecting damage. When we see radical changes in the gauge factor, that is when we expect the specimen to be damaged. So it can function not only as a strain detection mechanism, it can also function as a damage detection mechanism, which is also quite important. Of course, electrical transmission in a cementitious specimen is directly related to the water content. So we expect the electrical resistivity to increase as the curing continues. And we had a very remarkable, let's say, effect, where at the end of the hydration of the specimen, we had a very strong stabilization of the resistivity of the specimen. This was substantially affected by the presence of the carbon microfibers. Okay. Here we have in blue the typical curve that we expect from an ordinary cementitious specimen. Around 21 days, we have, let's say, the carbonation taking over from the hydration due to the low water content, and a stabilization of the electrical resistivity. And this behavior appears to be retarded in the case of the presence of the CMF Even in very small quantities, it can affect the hydration of the specimen. So we need to keep this in mind. But of course, the effect on the sensitivity of the specimen was enormous. We went from a gauge factor of around 50 to 133. So we managed to obtain a material that is far more sensitive in terms of sensing capabilities, which is exactly what we want to achieve. So we tried different series of conductive fillers. We tried graphite, we tried CMF, we tried nanotubes, and we managed to get, let's say, the percolation threshold for all series of fillers. So, and we can make quite an interesting comparison. In order to obtain the percolation threshold through graphite, we had to add around 10% of the weight of the cement in graphite, which is quite a lot, and it can affect many other properties. In the case of carbon microfibers, in order to optimize the piezoresistive performance, we only had to add 0.1%, which is nothing. In the case of nanotubes, we had to add around 0.2%, which is again nothing. Okay, I mean, nanotubes by themselves are also very cheap. It's just that the production process is very expensive and very difficult. But of course, these fillers, as expected, they do not only affect piezoresistive performance, they also affect physical performance. And the most radical effect that we saw was on the porosity. The addition of all of these fillers nearly always resulted in an increase in the porosity. Is that bad? Is it good? Well, mostly bad. Okay. Maybe it can increase a little bit the durability in freeze-thaw conditions. Maybe it can decrease the durability in the case of salt intrusion. Okay, so we need to balance these things out. We also try to, let's say, quantify and visualize the internal structure of all of these materials through microcomputed tomography. We managed to get some results and correlate them with the calculated porosity, not the calculated, the experimentally determined porosity. But the most important problem was that we were not really able to segment out the fillers that we had, especially the carbon microfibers. So there's a little bit more work to be done in that regard in order to be able to actually visualize and segment out the conductive fillers. Now, regarding durability, some more bad news. Water absorption was increased in the case of the presence of CMF for this material. Not by a lot, but for long-term durability, it can be quite detrimental. And we also checked, we did salt intrusion tests in order to directly test the durability, and we had sort of an interesting result. It turns out that the plain paste, when it is modified, it has higher durability, substantially higher, but the mortar has slightly lower durability when it is modified. Not by a lot, but it can be quite substantial. So I thought I was being very smart when I made these graphs to put everything in the same, but now that I look at it, it's very hard to understand what I wanted to say. But what I wanted to say, really, in the horizontal axis we have the concentration of the fillers, and in the vertical axis we have the strength and the Young's modulus. So we are mostly interested in the bending strength of the material. We do not expect it to work so much in compression, but rather we wanted to avoid tensile failure. And we're interested also in the Young's modulus. And in the case of all fillers, we had a notable increase in all of the properties. I think the most, let's say, impressive change that we had was in the case of carbon microfibers. We're adding a 0.01% led to an increase of almost 50% in the bending strength. So we add nothing and we get something very substantial in return. We also started playing around with something that ended up being very related to what Javier is doing. We wanted to see the effect on the ultrasonic pulse velocity of these modified materials. Okay, we had quite an obvious outlier in the case of the graphite, but the general trend is that the more fillers that you add, the more conductive filler that you add, even if you increase the Young's modulus, even if you increase a little bit the density of the material, even if you increase its strength, you get a notable reduction in ultrasonic pulse velocity. This was especially apparent in the case of carbon microfibers, where adding a 0.2% by weight of the binder, we had a 10% decrease in ultrasonic pulse velocity. I think the explanation for this is that we increase essentially the number of inhomogeneities in the material, so more opportunities for signal reflection and absorption. Okay, so even though we have a more dense, stronger material, we have a slower travel speed for the ultrasonic pulse. Okay, so we go through all of this trouble. We create these small little cubes. We have calibrated them. We know the gauge factor for this thing. So what do we do with it? Well, one solution, one possible option is to use it as an embedded sensor inside of a bigger structure. Okay, we take the initial calibrated sensors that we have tested in the lab, and we embed them inside of a larger concrete cast. Okay, so what does this give us? It gives us an embedded sensor inside of the structure that has a higher durability. It deforms thermally along with the surrounding structure, and it costs nothing essentially. But that is one option. I'm not sure that this is the best one. But these sort of sensors have in fact exhibited quite a strong sensitivity, not only to static testing, but also to dynamic testing. So even with a simple hammer test, we were able to pick up the induced strain in the material through this like kind of crude sensor. The more, let's say, optimistic or more ambitious application is to create entire structural elements out of these modified materials. Carbon nanotubes would be pushing it a little bit too far, I think, but graphite and carbon microfibers, they work quite well in that regard. And that gives you essentially a structural element that is a sensor of itself. You can measure through surface measurements of the electrical resistivity anytime you want, anywhere you want, strains, mechanical strains in the structure. And it responds both to static testing and to dynamic loading or cyclic loading. So it works quite well. You can have a distributed sensor with virtually no additional cost. I think the benefits are quite obvious for this. Now, my specific thing that I wish I could show you, but now we're doing the final experiments, is to use this sort of material as an embedded sensor in historic buildings. So what is the problem with historic buildings? You do not really have many choices on what material to use for intervention. On the other hand, when you have a historic masonry building, there is a specific intervention that you do quite often, and that is repointing of the joints. Repointing of the joints in historic buildings is done with lime mortar. So why not take advantage of this? And at the next repointing operation, we repoint with this sort of smart mortar in order to have a distributed sensor at the place where we need it. Okay. So we have a material that is slightly modified with carbon microfibers. The color is not that different. The strength is not that different. It is a little bit higher, but we do not want it to be too strong anyway. and it is a more efficient sensor of deformation. It is not as durable as the original material or as a new lime mortar, but that doesn't matter. I mean, repointed joints are a sacrificial layer. You're going to repoint them at some point anyway. So I think that is one possible way to have an embedded sensor system distributed or localized in a historic building, with the mechanical benefits and with the sensing benefits. So, regarding experimental testing and application, this is what I have for you. But I did promise, let's say, a few things about quantification or about understanding mathematically what is going on with these materials. Okay, so we're going into the realm of micromechanics of cementitious composites. It's really important to understand this in order to understand the physical phenomena of what is going on with these materials. So what we want to do is to modify, let's say, an existing material that features certain aggregates, pores, cracks randomly oriented within it in some sort of micromechanical context. And let's say inclusion-based micromechanics is a prime application for this sort of thing. We have, let's say, a homogeneous isotropic matrix with evenly dispersed inclusions inside it. Each one has its own aspect ratio, it has its own volume fraction within it, it has its own properties. Okay, this is exactly, this is a perfect description of what is going on in concrete or in mortar. So what we need to do is essentially couple two different physics problems in order to explain and quantify the piezoresistive effect in an existing material. So one way to do this is to take the composite material, calculate the electrical resistivity through homogenization methods, then apply a mechanical strain, calculate how it deforms, and then calculate again the electrical resistivity, but taking into account the various mechanisms that are introduced due to this mechanical strain. What does mechanical strain do in a material? It deforms all of the inclusions inside of it. It deforms the aggregates, it deforms the pores, it deforms the cracks. Okay, it changes the aspect ratio. And not only that, it can also change the apparent volume fraction of each individual inclusion in the material. When you have a relatively deformable matrix with a not so deformable inclusion inside it, like an aggregate, and you compress the matrix, the apparent volume fraction of the aggregate increases. This changes electrical resistivity. And this happens not only in the case of aggregates, it also happens in the case of conductive inclusions. This is the main mechanism that drives this part of the response. The thing is that in cementitious materials, we see an already quite high gauge factor, even in the absence of conductive materials. I mean, we can do a simple comparison. What is the gauge factor of a strain gauge? It's 1.4, 1.5, 2, something like that. In cement or concrete or mortar, it can be 10 or 50. Why does this happen? We need to explain it. One possible explanation is the mechanism of crack closure in a material that is compressed. We compress this material, we close a certain proportion of the cracks and create new electrical conduction avenues inside of the material. This reduces the apparent resistivity. And we can model all of this in a micromechanics context. We have to necessarily adopt a sort of statistical approach for this, because not all cracks have the same width, but they feature this sort of skewed normal distribution. We can take this into account into the model, namely we apply this much compressive force. What is the percentage of the cracks oriented in this direction that is closing, according to this distribution? We can model all of this quite easily. And in fact, achieve a gauge factor that is closer to what we observed in unmodified materials. Okay, so one way to discover what is going on with these materials and be able to quantify not only the piezoresistive effect, but also damage and strain, is through these simple micromechanics models. We're not there yet, but we are getting closer. So I think that's all I have for you. I didn't check time, we did not discuss it. Yeah. But for now, that's it. Thank you.